Hi everyone! Welcome to Elena Explains. I'm Elena and I'm here to be your resource on the AP Physics C Electricity and Magnetism curriculum. Today, we're going to be talking about the first topic, electric charge, electric force, and Coulombs law. So let's get into it. To talk about electric charge on an atomic level, we need to go back to the basics. I'm sure most of you remember from your chemistry classes that there are three types of subatomic particles: electrons, neutrons, and protons. Neutrons and protons weigh about the same with a weight of 1.67 times 10 to the negative 27 kilograms, while electrons weigh about 1,800 times less with a weight of 9.11 times 10 to the negative 31 kilograms. This is important to know later on in problems when we talk about force and when mass has to be taken into account, since some problems will try to trick you, since not all particles weigh the same. Another thing about these particles is they each have a different charge. Electrons are negatively charged, neutrons are neutral, no charge, and protons are positively charged. So I keep talking about this charge thing, but what is charge? Charge is a scalar quantity that can be either negative or positive, or neutral if it's zero. So charge pretty much talks about the extra amount of protons or electrons in an object. If an object has more protons, it's positively charged. If it has more electrons, it's negatively charged. And if it has the same amount, it is neutral. So when we're trying to find the exact quantity charge of an object, we need to look at its fundamental charges, or the elementary charge. So a proton and an electron has a charge of 1.6 times 10 to the negative 19 coulombs, which is the unit for charge. So for a proton, this value will be positive, and for an electron, that value will be negative. But instead of rewriting this number all the time when trying to figure out charge, we denote it by using the letter E. So a proton will have a charge of plus 1e, and an electron will have a charge of minus 1e. So if we look at this object on the left, this picture, this object has one proton, so that's plus 1e, and 4 electrons, minus 4e. So if we add those up, then we get a net charge of negative 3e. So this object is negatively charged with the charge has a value of negative 3 times 1.6 times 10 to the 19th. Now that we've established the definition of a charge, let's talk about different charged objects. So for an object to be charged, electrons must be transferred in or out of it. This is because when you look at the model of an atom, protons and neutrons are located in the nucleus in the center, while electrons circle the outside. Since they're on the outside, it is easy for them to go in between objects, So when we're talking about a charged object, it either has more electrons or less electrons. You wouldn't say it has more protons because protons don't move through objects. That wouldn't make any sense. So the first type of object that can be charged is a conductor. It's kind of in the name, but a conductor is an object that conducts electricity easily. This means electrons can transfer easily in and out and move throughout the object. Examples of this would be your metals like copper and gold. Many wires for electrical purposes are made of these metals. Also, water is a good conductor of electricity. You know how in the summer when there's a storm outside with lightning, they tell you, don't go in the water. This is because the electrons can easily transfer through water. Second type of object that can be charged is an insulator. Insulators actually stop electrical flow, which means electrons do not flow in and out easily. That means it's really hard to bring outside electrons in, and if the object is already charged, it doesn't really want to let go of those electrons. Some examples of this would be rubber, plastic, glass, or even wood. These really don't like to let go of their electrons or bring new ones in. Okay, by this point, we've established the definition of a charge, what it means for an object to be charged, and different types of objects that can be charged. So now, let's look at the three methods of charging. The first one would be charging by friction. So charging by friction starts with two uncharged insulators. In this example, we have an uncharged cloth and an uncharged plastic rod. What happens is you take these two objects and you rub them together for a while, and this rubbing motion creates friction, which induces the transfer of electrons between objects. So in the end, you'll end up with one object negatively charged and one object positively charged because the electrons from the positively charged rod or object moved to the one that is now negatively charged. So when you rub, no object will have the same charge every time. Like for example, this cloth, if you rub it against something else, it won't necessarily have a negative charge again. It's all random, you won't know until you test it. And only insulating materials can be charged this way. You cannot do this with like a metal rod or something like that. Now, the second method of charging is charging by conduction. So charging by conduction typically starts with one uncharged conductor and one charged conductor that are touched together so they can share that charge. This sounds a little confusing, but look at the images. So in the first one, rod A is neutral, while rod B has a charge of -6. Then, in the second image, they're touched together and they share a charge of -3. They each have a charge of -3. So basically, after contact, the charge of each object is half of the difference of their charges initially. So in the initial image, the difference would be 6 because this one's -6 and this one's 0. And then now they each have -3, which is half of that difference. So the last and probably most complicated way to charge is charging by induction. Before we get into charging by induction, it's just important to know that like charges repel and differing charges attract. So an electron will repel an electron, a proton will repel a proton, and an electron and a proton will attract. So now let's look at our image here. So we start off with a metal sphere, neutrally charged, and we bring a positively charged rod near it, not touching, just near it. Within the atoms of the neutral sphere, since it's not touching, the charge cannot just directly be transferred. However, the negative particles within that sphere will tend to move closer to the positively charged rod, while the positively charged particles within the sphere will tend to move away from the rod, just turn away to face the rod. This is a process called polarization, and this happens when the objects are not touching. So this happens while the rod is near. Then what happens is the sphere is connected to the ground through a grounding wire. What happens when you connect the sphere to the ground is that since the ground, it has protons, it has electrons, since it has atoms, the negatively charged electrons will move up through the wire towards the positively charged rod. Then finally, when you disconnect the rod, all those negatively charged particles are staying there because they want to be near the positively charged rod. And finally, when you move the rod away, you're left with a negatively charged sphere. This can even work in the opposite. If you bring a negatively charged rod near, then electrons from the sphere will just move into the ground, to get away from the rod. And then when you disconnect, then you're left with a positively charged sphere. So now that we talked about electrical charge, let's switch gears a little bit and talk about electrostatic force. Electrostatic force is pretty much the force exerted by an object based on its electrical charge, whether it be positive or negative. You can't really talk about electrostatic force without mentioning Coulombs law, which is this equation I have up on the screen. F of E equals 1/4πε0 times the absolute value of Q1 times Q2 over R squared. Sounds complicated, but let's break it down. So F is force, we all know that, and the little E at the bottom just indicates its electrostatic force, dealing with electricity and charges. Then equals this 1/4πε0. So this whole value, 1/4πε0, can also be denoted by the letter K. You'll see that a lot too. And that whole thing has a value of 9 times 10 to the 9th. So if you're wondering what this little epsilon thing is, that's just the value that is used for the value of vacuum permittivity, but we don't have to worry about that right now. You just need to know that that whole thing is the same as K, which is the same as 9 times 10 to the 9th. So when you're doing your calculations, just use 9 times 10 to the 9th. Then we have Q. Q is the charge. And since usually we're dealing with two objects, like the electrostatic force exerted by one object on another, you need to put both of those. And you don't really account for negatives and positives in this equation, so you just put the two numbers, the absolute value of that product. And that's all over r squared, which is the distance between the two objects, or the distance between the particles. Obviously, we know force is in newtons. This 1 over 4 pi e, that's just a value. Q is in coulombs, and distance is always in meters. So be careful in problems when they're telling you different Newton units to make sure you use the right one. So that's it for today, guys. If you want to see some examples of these concepts being applied, that'll be in the next video. But for now, I'll see you all later, and thank you.